then let me start talking about pseudopolynomial-time algorithms for optimization problems. And by optimization problems, I mean really classic optimization problems like subset sum, knapsack, and later on a little bit of integer programming and scheduling if I get to that. Right, so subset sum, you all know it, right? This very classic NP-hard problem. I will always talk about being given a set X of n positive integers and some target value t, and we want to know whether there is a subset that sums to the target value. So for example, in this little example here, yes, there exists a subset summing to the target. Yes, so for simplicity in the whole talk, I'm assuming that X is a set. In particular, this allows me to drop n sometimes when I can upper bound it by t, because I cannot assume that all of these given integers lie between 1 and t, and each one is unique. So, anyways. One way we teach dynamic programming is this very simple pseudopolynomial-time algorithm for subset sum that solves it in time n times t, right? You build this big table that stores for each of the first I items, whether it sums to some number s, and you can fill each table entry in constant time, so you can solve it in time n times t. And this kind of algorithm is called pseudopolynomial because its running time depends on t, which is not bounded by the input size, right? It's not bounded by the number of items. It's also not bounded by the total number of bits of the input integers, because this would just be n times log t. So in this sense, it's a pseudopolynomial algorithm because it depends on the running time depends on a numeric value of the input. Good. So now we've fixed a parameter, taking the viewpoint of parameterized complexity. We've fixed a parameter t now. Let's determine the optimal running time in terms of t. And also, let's for the beginning of this talk, let's ignore polynomial factors in n, which I mean, also for lots of people in the audience should be natural. Right. So in particular, we ask whether time t times poly t is optimal, or whether the dependence on t can be improved, say to log t, or maybe just a square root t or something. And on the other hand, if we cannot improve it, can we prove conditional lower bounds? What do I mean by conditional lower bounds? Well, anything that starts from a plausible hypothesis and reduces the problem that the hypothesis is about to subset sum, thus obtaining a conditional lower bound for subsets. Classically, you would start from the hypothesis that p is not equal to np, meaning that satisfiability is not in polynomial time. And then you would prove NP hardness of subset sum by reducing satisfiability to subset sum. And generally, this way you can prove lots of super polynomial lower bounds, right? Assuming that satisfiability is not in polynomial time, lots of other problems are not in polynomial time. And of course, this has been done very classically by Karl for subset sum. It's already one of the first problems that have been shown to be NP-hard. So it's not in time poly n and log t, so you cannot improve the dependence on t to poly log t. Right, now in the last 20 years or so, stronger hypotheses came up, right? Like the exponential time hypothesis, stating that satisfiability is not in time 2 to the little of n, or more precisely, resat is not in time 2 to the little of n. And if you combine this with reductions, then you can prove lower bounds that are tied up to the constant in the exponent. So if you ignore what is the exact constant in the exponent, you can prove tight lower bounds. And of course, this has also been done for subset sum, being a classic target for these kinds of things. So independently by Bringmann et al. And Jensen et al., it has been shown that subset sum is not in time t to the little of 1 times 2 to the little of n. So if you want to improve the dependence on t to subpolynomial, t to the little of 1, then you have to pay an exponential factor in n, one way to interpret this result. All right, and then there's one stronger hypothesis called the Strong Exponential Time Hypothesis, which roughly speaking states that satisfiability is not in time 1.999 to the n. More precisely, it states the following, that for any epsilon that you pick, there exists a case such that k side is not in time 2 to the 1 minus epsilon n. And this really conjectures something about the exact constant and exponent, right? It's really 2 to the 1 times n. It's not 2 to the 1 minus epsilon times n. So having a hypothesis that states something about the correct constant and exponent, we can also try to actually prove lower bounds that have the correct constant and exponent. And indeed, 2 years ago, we did this for subset sum, at least with respect to this parameter t. Namely, we showed that subset sum is not in time t to the 1 minus epsilon times 2 to the L of n. So for any epsilon that you pick, you cannot improve the dependence on t to the minus epsilon unless you pay an exponential factor in n. Okay, here's one different way of writing this lower bound. If this 2 to the L of n is maybe not intuitive enough, then here's a different way of writing the same lower bound. Namely that for any positive epsilon that you choose, there exists a positive delta, such that you cannot solve subset sum in time order t to the 1 minus epsilon. And this holds even on instances that have just delta times log n many input numbers, many items. Okay, so if, in particular, if you would have, so this 2 to the L of n factor would just be t to the L of 1, so it's a negligible factor for the hard instances that are constructed in this reduction. All right, so we cannot improve the dependence on t to sublinear even if we just have a logarithmic number of items. So if we come back to this question here, is time t times poly-n optimal? Then yes, essentially it is, assuming the strong exponential time hypothesis. Cannot improve it, cannot improve the dependence on t to the 1 minus epsilon. And that even holds if we relax this poly-n factor to 2 to the L of n factors. Let me also mention here that strong exponential time hypothesis, this is the most standard assumption to prove these kinds of lower bounds. There are other hypotheses, like the set cover hypothesis, and this lower bound of the form t to the 1 minus epsilon times poly-n has been known before under the set cover hypothesis. Now it's known under the more standard SETH, and it's even known with this 2 to the L of.
Karl?
All right.
Yeah. I'm just curious, do we have like a conjecture as to what the dependence on n should be if you don't worry about t? Like, is it better than 2 to the n over 2 or something?
Right, this is a big open problem. So whether like subset sum can be solved faster than meet in the middle, faster than 2 to the n over 2, like if you, that's a big open problem. I know people in the audience that have been working on this for many years. Yeah, no, I don't have any answer to this. Only is in this parameterized setting where we look at parameter t, we know this tight lower. Right, you all know NP hardness proofs of subset sum. If you've most likely seen it, right? What do? You start from satisfiability somehow and encode. You can either encode settings of variables as items. You can also encode assignments of clauses as items. And then you need to somehow check consistency or check that all the clauses are satisfied, which you do in like different bit blocks that are spaced apart enough. And so it's not so hard to do this. So what are the new ingredients to get a tight lower bound? The most important one is this notion of an average free set, which is the following, that a set of integers A is called average free, K average free, if whenever you pick K plus 1 numbers in A, so x1 to xk and x, if the first K of these numbers sum to K times the last one, or in other words, if the average of the first K numbers is equal to the last one, then actually all these integers already had to be the same. You can interpret this as some kind of consistency check that is this enforces, like you choose k items, and this enforces that all of them have to be the same. And a very classic construction in additive combinatorics from 80 years ago, 75 years ago, shows that there are very large average free sets, or there are average free sets over a very small universe. Namely, universe size is just n to the 1 plus epsilon, where n is the size of A. N to the 1 plus epsilon times some dependence on k and epsilon that we usually don't care about. So what's the intuition why average free sets exist? Well, if you look at vectors, if you look at unit vectors, we want to have average free sets over the integers, but let's focus on a different kind of object now, namely vectors, unit vectors. Then it's pretty clear that they are average free, right? You take a unit vector and you add it up k times, and you end up at a vector that has length k. But if you take any k unit vectors that are not the same, then you end up at a length less than k, strictly less than k. So, so if you want to check whether the sum of k unit vectors is equal to k times a unit vector, well, this can only be the same if this can only be the case if all these unit vectors are the same. Okay, so for vectors, this is easy to see, and then this construction by Behrendt, first of all, it looks at vectors with integer coordinates and shows that there are sufficiently many, and then it embeds vectors into numbers, into integers, by just writing the components of the vector in different bit blocks and having a bunch of padding zeros to avoid overflow. So it's not hard to do, but yeah, that's the rough intuition why these kinds of objects exist. Good. Now, if we have average free sets, how does it help for proving reductions to subset sum? Well, I already mentioned that this can be interpreted as a consistency constraint. If we have k+1 variables and we want to check whether all of them pick the same value, then we can do this by embedding these values, by replacing these values by the average free set. Instead of number I1, let's take the I1th element of an average free set A. Right, if you replace I1 by its corresponding number in the average free set and so on, and you replace I by well, basically k times the ith number in the average free set, then the sum of all these entities here is equal to some target, if and only if all these numbers were the same. Right? This, this k times u minus is just to make everything a positive number. So the k times u actually cancels. And what is written here is exactly the condition of an average free set, so this condition here. Right, meaning that you can check an equality of k+1 numbers in a range from 1 to n by writing down one sum constraint. And right, so you can check the consistency of k+1 numbers between 1 and n by using a sum constraint on a small number of bits. Number of bits is just a log of the universe size of Behrendt's construction. So this is just 1 plus epsilon log n plus something depending on k and epsilon. And normally when we use this, then this dependence on k and epsilon is negligible. We just get this 1 plus epsilon log n. And well, log n you certainly need, right? If you want to check consistency, if you want to check whether two numbers in the range 1 to n are equal, you need to check certainly log n bits that they're the same. So it makes a lot of sense that we need at least log n. And this gadget here gives us basically just a 1 plus epsilon overhead. which means that it's a very tight consistency constraint, and it uses basically the minimum number of bits that you can hope for. Okay, and then just as a very rough overview now, how do we use this in a reduction? Let me just give you an example. Let's say, suppose that you want to reduce k-clique to subset sum. We are given this graph, say 4-partite graph here, in general k-partite graph, and you want to select a k-clique. You want to find a k-clique. So in each part, you want to select one vertex, and all of these vertices are pairwise adjacent. And then what we do is we create one item for every edge in this graph. So every green edge here will become one number, one item. Then there are two types of constraints that we need to enforce. One is that we pick one edge between any two parts. So we pick one green edge. We pick these 6 green edges that I've drawn here. So we pick one edge from every part. And for all the edges that leave one part, so these 3 edges, for example, we need to check that their endpoints are consistent, right? That all these edges choose the same endpoint, so that the union of these edges actually forms a k-clique. Okay, and now I claim that we can write down all these using only basically k-log n bit numbers. Right? So what are so how many bits do we need to enforce these constraints here? So that for each so for this first constraint, that for each pair of parts we pick an edge, basically this means that for each pair of parts you will have a bit block, and the edges that belong to this have a 1 in this bit block, and the target has a 1 in this bit block. So you have to choose one item of this type. You have to pick one edge for every part, and this basically gives you poly k over epsilon bits. And then we need the consistency, and for this, of course, we use now the consistency constraint that we get from Behrens' construction, namely for each of the k vertices that we want to choose, we have k-1 candidates, and we want to check that all of these candidates are the same. And we do this in a separate bit block for each vertex. So we get k bit blocks, and each of them just has the size of Behrens' construction. All right, and now, I mean, if you want to have running time better than t, it means you get running time better than 2 to the log t. So you get running time better than 2 to the whatever this is, which is basically n to the 1 plus epsilon k, right? So if you get running time much better than t, then you for subset sum, then you also get running time much better than n to the k for k-clique. Now this alone is not yet surprising, right? Because we know how to solve k-clique using fast max multiplication better than n to the k. But that's why I said this is only an example to give you some intuition how this kind of reduction works. What you can do now is to generalize this reduction to hyperclique, and then there is a reduction from SETH to hyperclique, and then you get kind of what I claimed. Anyways, just as a very rough overview. Right. So this, anyways, that's a rough overview of how this lower bound works. Good. So we know that subset sum is in time n times t. It's not in time sublinear in t. Even if you pay, or if you want sublinear in t, you need to pay an exponential factor in n. Now, subset sum is a special case of lots of other optimization problems. So as soon as you get a lower bound for subset sum, you get a lower bound for many other problems. So for example, for example, you can just look at other parameters for the subset sum problem. So other parameters that make sense are, for example, the maximum input number instead of the target number, or the sum of all input numbers. For many of these parameters, they are actually polynomially polynomially related to the target, right? The maximum input number certainly is at most t, because we can ignore all input numbers that are larger than the target. And a target can be at most n times the maximum input number, because otherwise we certainly cannot reach the target. So the maximum input number and the target should differ at most by a factor n. And for any parameter p that is polynomially related to the target, we obviously get the same result. Right? You can solve it again in time p times Polyend, because p is the same as t up to Polyend factors. And you also cannot solve it in time p to the 1 minus epsilon times 2 to the little of n, again, because p is polynomially related to the target. And similar things happen if you go to other problems, like for knapsack problems. Well, it's a generalization of subset sum, in the sense that there is a trivial reduction, or like a very simple reduction from subset sum to knapsack, which replaces the target number as a parameter by the weight budget W as a parameter. And in the reduction, they just turn out to be the same. So W is set to be equal to T in the reduction. And I mean, classic dynamic programming algorithms solve knapsack in time W times n, so in particular W times Polyend. And if you would solve it faster than, if you would solve it in time W to the 1 minus epsilon times 2 to the little of n, then just by this reduction from subset sum to knapsack, you would violate this lower bound for subset sum. And the same applies to lots of other pseudo-polynomial time settings of scheduling problems or some forms of integer linear programming or so. So oftentimes there is this natural, or there are some natural pseudo-polynomial parameters, and we now know that you need this linear dependence on this parameter. Okay, so that's all nice and good, but we ignored the Polyend factors, right? And I mean, I come from fine-grained complexity, where oftentimes I'm studying actually polynomial time problems and proving like n-squared lower bounds and this kind of things, where I'm used to not ignoring the Polyend factors. So in the remainder, I will actually look at these Polyend factors, and then things become very interesting and much less understood. Right. So we've seen these two things. For subset sum, it's in time nt and not in time sublinear nt. You can actually, if you're wondering, you can also not, I mean, the first lower bound is showing that you cannot shave off a t to the epsilon factor. One can also argue that you cannot shave off an n to the epsilon factor. And this is basically just by adding enough dummy items so that the running time of the second form would imply a running time of the first form. So we can neither shave off t to the epsilon or n to the epsilon. So t is really the right running time we should hope for. But there was this annoying factor n until some time. Until first of all, Kiliaris and Xu, they improved this to root n times t. And then I shaved off even more. Big difference is that the best known deterministic algorithm is still the square root n times t. And everything that came afterwards is randomized. Right. So I showed this with a couple of log factors. The number of log factors was improved by Jin and Wu. So now you can solve subset sum in time t log t. And we have these matching lower bounds, right? You can, from this t log t running time, you cannot shave off a t to the epsilon. You can also not shave off n to the epsilon. So this is a conditionally optimal algorithm in some sense. It's tight in the dependence on t as well as in the dependence on n, up to lower order factors and assuming SCTH, of course. Right. So this, let me tell you a little bit about this algorithm here, right? Because it's using, it introduced this kind of, you can view it as introducing a kind of framework that has been used lots of times afterwards. And this is based on convolutions. What's a convolution? So here we're given two arrays of length n, a and b. We want to compute a third array c, such that the kth entry of c is the following. Well, we fix these two operations that we call them plus and times, but it can really be any operations. And what you want to do is to take the plus operation over all index pairs I and j, such that I plus j is equal to k. And you take the times operation of ai and bj. So naively, you can certainly compute this array C in time n squared, right? Just by evaluating this. So assuming that these operations can be evaluated constant time, you can compute C in time n squared just by evaluating this definition. But of course, there are well-known convolution problems that can be solved faster. So if these operations are really normal plus and normal times, then this is standard convolution, and this is just a different description of polynomial multiplication, and it can be solved in n log n time by fast Fourier transform. And similarly, there are some other easy types like or and convolution. It's the Boolean convolution, and this you can reduce to standard convolution, so it can also be solved in time n log n. And this one is equivalent to sum set computation, if you want. So a sum set is the following, that you have two sets of integers and you compute the set of all pairwise sums. So set of all sums a plus b, where a comes from the first set and b comes from the second set. And this is the same as Boolean convolution. If you look at the indicator vector of a, the indicator vector of b, and then the indicator vector of their sum set is the Boolean convolution, the indicator vectors of a and b. Right, so these are easy convolution problems. There are also some hard ones that we will encounter later. Good, and this approach that I've been talking about consists of a partition step where we randomly or mostly randomly split the problem into two or more subproblems, and then we combine the subproblems by the appropriate convolution problem. So for subset sum, the appropriate convolution is just taking the sum set, or actually more precisely, it's the capped sum set. So a plus tb, I will denote as the sum set of a and b, but we ignore everything that is larger than the target, right? Because in subset sum, we are not interested in any subset sums that are larger than the target. And this you can solve in time t log t. Because a and b are subsets of the integers from 0 to t. You can compute their sum set in t log theta. I will also use this a0 notation as by just adding 0. It's also motivated for subset sum because you always have the empty set. So you can always create subsets that sum to 0. All right, now why is this operation useful for solving subset sum? Well, if you take your input items x and take the sum set with itself, then this is not useful because it contains forbidden sums, right? In x plus x, you could take the same x in the first summand and the same x in the second summand and take their sum, but this does not correspond to a subset sum. What you can do, though, is to partition the input items, let's say in two parts, x1 and x2. And then if you take the sum set of x1 and x2, this only contains valid subsets. And our goal will be this, to compute the set of all subset sums below t. Set of all, take a subset y of x, you take the sum of y, but you only keep the ones below t. This is what we want to compute now. And this is done in two steps. The first one is inspired by color coding from parameterized complexity. right? And this is used to detect sums of small subsets. So all the subsets that sum to at most t and are small, namely contain at most k items. Right? How do we do this? We randomly partition the input items into k-squared parts. So each input item chooses a random number between 1 and k squared, and it falls into the corresponding bucket xi. Okay, and then after random partitioning, we just compute this expression here, meaning that to each bucket xi we add 0, and then we compute the t-capped subset of all these buckets. Okay, now what happens to a subset of size k? Suppose we have this subset y consisting of k items. These items are somehow randomly distributed over these buckets, right? And it can, of course, happen that 2 items land in the same bucket, and that would be a bad event. Then the set y is not split. That's a bad event. Then let's look at the good event, namely that the set y is split, meaning that every bucket contains at most 1 element of the set y. And then we're in the good case, right? Then the sum set that we compute will contain the sum of this subset y, right? Because in this subset, we can pick any item in here. In particular, we can pick y3. And pick any item in here. In particular, we can pick 0 because we added it explicitly to each bucket. So in doing this, we can pick all the items of y in the buckets that contain some items of y, and we can pick 0 in the remaining buckets. So the whole thing will just sum up to just total sum of all the elements of y. Good. So if y is split, then we compute its subset sum. Now, of course, now we have to analyze the probability that we are in a good event, that y is split. And this is basically the birthday paradox. By throwing k balls into k-squared bins with constant probability, this set is split. Okay, and once you have constant probability, we just repeat log n times to boost the success probability. So the color coding procedure just repeats log n times, it picks a random partitioning into k-squared parts, adds 0 to each part, computes the t-capped subset of all parts, and in the end, we return the union of all the sets that are computed. Now, this only computes valid subset sums, first of all, because we take a partitioning and the sum set over parts that only can only create valid subset sums. And for each small subset consisting of at most k items, with high probability, we compute its sum. This is the guarantee of this procedure, and it runs fast. So up to log factors, one sumset operation just takes time t up to log factors. We have k squared of these, so the rank time is t times k squared. And it follows this partition and convolution thing, right? We partition into k-squared random parts and convolve using the sumset operation or Boolean convolution, if you will. Okay, that was the first step to find the small subset sums. The general second step is a recursive thing. Suppose that we have our set of items x and fix some subset y that sums to at most t. And what we do is we split x into the large items and the small items. Large here means more than the target divided by polylog n. Right? And then we handle the large items and the small items separately. So on the large items, we can run color coding, right? Because any solution can consist of at most polylog n many large items, because that's how we defined when an item is large. So we can run the color coding procedure with k being polylog n. then with high probability, we will find the sum of the large items among Y. This sum will be contained in the output of this color coding procedure. Now, the small items, we randomly partition into two parts. So XS, those are the small items. Each item in XS randomly is assigned to either X1 or X2. And this, again, splits the small items in Y into Y1 and Y2. Now, because these items are small, we can show concentration there. We can show that, certainly in expectation, the sum of Y1 and the sum of Y2 should be at most T half, right? Started with the set summing to at most T, we split it into two halves at random. On expectation, the two halves can sum to at most T half. But because this, all these items are small, you can show some kind of Chernoff-like concentration that this is actually very close. This has to be close to T half with high probability. And we're losing just this 1 + 1 over log n factor. And similarly, also the number of items in the two random halves drops by about a factor 2. And we recursively solve both random subsets, x1 and x2, but now with a smaller target number. The target number can drop to essentially T half. Okay, and this recursively we get two sets of sum sets, two sets of subset sums, S1 and S2. And we simply return the sum set S1 plus S2 plus SL, which came from the large items. Good. Then, if you think about it, this gives rise to following kind of recursion for the random time. Directly we spend time near linear and T to compute the sum set in the last line. And then we have, and also this color coding procedure here runs in time near linear and T, because the running time was T times K squared, but for K we plug in a polylog n factor. And then we get two subproblems where the number of items is basically n half and the target is basically T half. Then you need to argue that this 1 + epsilon factor doesn't hurt, but essentially what you get is that this kind of recursion and this is a well-known recursion here, right? That you just get another log factor on top of what you already had. You have two subproblems of half the size, you just get another log factor on top. The total running time is again near linear and T, with a bunch of log factors that I'm ignoring. Good, and again, this was a partition and convolution, right? We take out the large items and the small items, we randomly partition into two parts, and then we combine everything using the appropriate convolution, which in this case is computing the subset. All right, so this was an overview of how you can solve subset sum in near linear time in T. So this gives us this conditionally optimal algorithm, right? You need time near linear in T. You cannot shave off T to the epsilon. You can also not shave off n to the epsilon. Can we generalize this to other settings and other problems? So. Of course, the lower bound that we have for subset sum, this directly transfers to the generalizations, but it's not necessarily tied for the generalizations, right? So it's not clear whether we can obtain similarly conditionally optimal algorithms also for other settings and other problems. But it's also not clear whether this a priori, whether this partition convolution approach is applicable. Of course, lots of these generalizations have been studied in the last years, like for Knapsack and approximation of subset sum and so on and so forth. Actually, for many of them, this partition and convolution approach was central to getting either a hardness reduction or an approved algorithm. And I want to discuss some of these applications in the following. The first one is other parameters for subset sum. we have this conditional optimal algorithm in terms of parameter t, but there are other parameters that make sense, right? For example, you could look at the largest input number, max of x. Let me denote this by s. So as I argued before, s and t are polynomially related. All the input numbers should be at most t, so s is at most t, and the target has to be at most n times s, otherwise it's not reachable. So they are polynomially related, but this doesn't tell us anything when we now actually consider the polyend. Now, okay, the lower bound directly transfers because the lower bound is in the case where the number of items is just logarithmic in the parameter. So then this relation is tied up to a log factor, so then the lower bound actually transfers. You cannot solve it in time in s to the minus epsilon times 2 to the little of n. But what is known? So of course you can solve it in n times t. Piesinger showed that you can solve it in n times s. Then you can also show it in, and n times s is always better than n times t, or asymptotically dominates n times t, or however you want to call this, just because s is at most t. And you can also solve subset time in time near linear time in t, and up to log factors, this dominates the n times s running time, right? Because t is at most n times s. Now the natural next step would be to get running time near linear in s, and this is widely open, and I would say it's the most important open problem in this line of research, whether you can solve subset sum in running time, just s times log factor, s plus n, I guess. Yeah, and this s. It's not even known, as far as I know, whether you can solve it in time n to the 0.99 times s, by the way. Good, so that's a pretty big open problem, and we are very far from solving it. There are some curious things going on in this parameter s. So for example, if you look at the case where s and t are polynomial in n, which, I mean, not clear how a realistic scenario this is. Certainly it's one of the cases that should be handled if we want to get an optimal dependence on s. Now in this polynomial, in this dense regime where s and t are polynomial in n, there was this old line of research that showed that when the target is big enough, it's at least s squared over n, and you can solve subset sum in time n plus s squared over n squared. And this somehow was a line of research that used additive combinatorics. Particularly, it was using that if you have a very dense set of the numbers between 1 and n, and you look at its set of all subset sums, then this contains a long arithmetic progression. Which, I mean, a priori is a purely mathematical statement about dense sets and their set of subset sums, but it can be used algorithmically to show this kind of result. In particular, I mean, for larger target, you can use the near linear in t algorithm. If you combine the two, then you can solve subset sum in time s squared over n plus n, and this doesn't have any condition. So this kind of curious running time is possible. It's not yet, I mean, it's not saying that you can solve it in time s. Yes. Now what we recently did is to refine this approach and show that you can actually improve the running time from n plus s squared over n. You can improve it all the way down to just near linear in n with the same condition that t is at least s squared over n. And we also showed that you cannot solve it in linear time in n. So there's a superlinear lower bound when t is much less than s squared over n. So in other words, this tells you exactly when dense subset sum can be solved in near linear time. The characterization of all the parameter settings where dense subset sum can be solved in near linear time in n. Right, which again is a curious result in a certain regime, but doesn't tell us the whole story. Of course, I mean, I was asking about what's the optimal dependence on S. You can also ask for the optimal dependence on S, T, and N. My conjecture is that the optimal running time should be this, S squared divided by T plus N. But who knows? I mean, we do have in this paper with Philip Wellnitz, we have a lower bound of S squared divided by T plus N. I mean, my intuition would be that this lower bound is tight, but we are nowhere close of having a matching algorithm.
Karl?
Yes?
The results from your recent paper, is that for the case S and T being polynomial in N, or is that with no restrictions?
Yes, so this condition that T is at least S squared over N, it can only hold for a relatively small S and T.
Ah, okay.
Right. Okay. So it only works for polynomial S and T. But the lower bound holds more generally. This is we proved this S squared divided by T lower bound, and this holds wherever you want.
Can you maybe say briefly something about why it helps that your target is large? It's kind of counterintuitive in comparison to the previous runtime.
So it helps if the target is close to half the total input sum. Basically, this kind of additive combinatoric stuff, you can use it to show that for a dense subset, for a dense set of integers, basically all the numbers. Okay, actually, if you have if you are in this dense regime, and I mean, there's some technical condition that it's not true that all of your items are divisible by some common denominator. So let's ignore that. If this is not the case, then basically all the numbers can be written as a subset sum. All the numbers, meaning all numbers that are sufficiently close to half of the total sum of the input. And sufficiently close turns out to be this constraint, that the target is at least S squared over.
Yeah, in your first sentence, I already, in your reply, I already thought, oh, okay, yeah, when it's close to half, you're bound to have a solution unless something special happens. But it's exactly. only a lower bound, right? So what if T is even?
Yeah. So these things here, sorry, yeah, I forgot to mention this. We are always assuming that without loss of generality, T is at most half the total input sum. Right, because there's a symmetry in subset sum. When the target is more than half, then you can just look for the complement of the set that you're looking for. Yes, sorry.
Yeah. Okay, thanks.
If T is at most half the total input sum and it's much more than S squared over N, then you get this kind of result. All right, how much time do I have now? 5 minutes? No. Wait.
Minutes. Yeah.
10 minutes? Okay. Good. Right, this was subset sum with other parameters. Now, knapsack problem. So this is one way of writing the knapsack problem, maybe not the most intuitive, but the one that makes sense for what I want to tell you. So now we have a set of n items. Each item has a weighted profit. We have a weight budget. And what we want to compute is fx of w, where fx of I is the function that for each weight budget I tells us the maximum profit that we can have with weighted most I. Okay, so this fxi somehow naturally describes all the optimal solutions of knapsack, and we want to compute the optimal solution with weight budget w. Can solve this in time n times w, classic dynamic programming. Actually, a variation of this gives time n plus w squared, because for each particular weight, for weight I, you only need to store the W over I best items of this weight. You can ignore all the other ones, and if you to think about it, then this leaves just basically W times log W many items that you're left with, and that ends. And so Bellman after preprocessing gives n plus W squared. It's a generalization of subset sum, so you cannot solve it in time sublinear n W times 2 to the log of n. And of course, we can ask whether the same kind of improvement as for subset sum is also possible for knapsack. So whether we can get time near linear in W or n plus W. So let's try this partition and convolution approach. So what we do is we split the items into two subsets. We recursively compute their solution functions, fx1 and fx2. And then we want to compute the solution functions of the subproblems to the solution function of the original problem. What does this combination step look like? Well, if we want to have, if in total we want to use weight budget k, then we can in some way split k into weight budgets into I and j, such that I plus j is equal to k. And we can allocate weight budget I to the left subproblem and weight budget j to the right subproblem, and maximize the profit in the subproblems. So maximizing over all I and j that sum to k of this fx1i plus fx2j, this certainly gives the solution function of the original problem. Okay, now this is not exactly the same convolution as we had before. Now it's a max and a plus here as the operations. Let's get back to the convolution problems that we looked at. Now these operations are max and plus, and actually the more standard notion to look at is min plus convolution. But this is equivalent after just negating all the input numbers. So max plus and min plus is the same. Min plus convolution is a very well studied problem again. Naively, you can solve it in n squared time as all the convolution problems, but the best known is not much faster than that. You can shave off this 2 to the square root n factor, but this is all that's known. In particular, there is the min plus convolution hypothesis stating that you cannot solve this in n to the 2 minus delta in a positive constant delta. All right, so the min plus or max plus convolution, this is an example of a hard convolution problem where basically the naive n squared is the best we know. Okay, so the natural combination step for the knapsack problem is min plus convolution, and this is one of the hard ones. If you go through this, then well, you will need this time W squared to do the combination step. So you can reinvent this Bellman with preprocessing running time of n plus W squared, but that's all that you get from this partition and convolution approach. Well, except that you can, if you want, you can shave off this 2 to the square root log W factor. So anyways, if you want, you can do it. Good. So this only reinvents this Bellman after preprocessing. But actually, so if you think about it in a different way, you can also view this as a reduction from knapsack to min plus convolution. And there's also a reduction in the other way around. And what you get from this, and what Seigen et al. And Köhnemann et al. Showed, is that you can solve knapsack in time n plus W to the 2 minus delta, if and only if you can solve min plus convolution in subquadratic time. And well, there's a hypothesis that you cannot do the latter, so you should also not be possible to do the former. In particular, knapsack is harder than subset sum, right? For subset sum, we got near linear time in n plus t. For knapsack, it's not possible to get near linear time in n plus W, assuming the min plus convolution hypothesis. Now, is this the last word on knapsack? Not really, because right now we don't know whether this kind of running time is possible, n squared plus W. It's not ruled out by this min plus convolution lower bound. It's also not ruled out by the SETH lower bound, but it's also far from the upper bounds that we know. So this is, the truth lies anywhere between this and the upper bounds that we know. Good. And Another interesting example is Bicriteria Path. Another classic optimization problem, right? Given a directed graph, each edge has a length and a cost. You have a source vertex and a sink vertex and a cost budget. You want to compute a source to sink path that has total cost at most the budget C. And among all these paths with total cost at most C, it should have minimum total length. Okay, there's a classic dynamic programming solution that solves this in time n times C. Basically, you should just compute for each vertex and for each cost, what's the minimum total length to reach this vertex with this cost. Very, very straightforward. It's a generalization of even of Knapsack, but also certainly of subset sum. So clearly you cannot solve it in C to the n minus epsilon times 2 to the little of n. And really just this follows formalizes this simple reduction from subset sum to Bicriteria path. You can create like two edges for each item in your subset sum instance. One edge corresponds to picking this item, the other edge corresponds to not picking the item. And then you set the length and the cost in such a way that the total cost will just be the sum of the subset that you pick. So if your cost budget is the target T, certainly you want to select a subset summing to at most T. And the total length corresponds to something minus the total sum of the items. So minimizing the total length means you want to maximize the sum of the selected items. So if there is a subset summing to T, then this is an optimal solution. So an easy reduction from subset sum to Bicriteria path, and this shows this lower bound. We can actually show something more, namely that I mean, you cannot hope for sublinear dependence on C, but even if you look at linear dependence on C, then you need to have an additional factor n of the running time. Roughly speaking, why do we get a higher lower bound? Well, so this reduction, so in subset sum, the number of items n was just this delta times log t, right? Logarithmic in the target. So the number of vertices that are created in this reduction is really small. It's just logarithmic in t or logarithmic in c. If we want more vertices in our graph, then what we can do is to simulate more instances of subset sum. Right? If I'm given many instances of subset sum, then I can write down the gadgets for all these instances of subset sum and connect them to a super source and a super sink. And then Bicriteria path in this instance encodes whether at least one of the given subset sum instances was a yes instance. Okay, and what we do is to prove that the OR of many subset sum instances cannot be solved faster than trivial, basically. And this gives this kind of lower bound that if you can essentially simulate n or n by polylog c many subset sum instances, so you need this running time. Okay, so the lower bound actually also works for us. I mean, the lower bound constructs a sparse graph, and the upper bound is also just n times c on sparse graphs. So on sparse graphs, this running time is conditionally optimal. It's open though what happens in slightly denser graphs or much denser graphs. So what's the correct dependence on m in C? This is open. Right. It's also not well understood for other parameters. So for example, if you look at the sum of all edge costs as the parameter, we don't know what is the correct polynomial dependence on. Good. I guess I should come to an end. There are lots of other topics. For example, approximation schemes are related to pseudopolynomial-time algorithms, right? Because if you have a 1 minus epsilon approximation and you set epsilon to be 1 over the target roughly, then you solve subset sum exactly. So whenever you have an approximation scheme, it implies a pseudopolynomial-time algorithm. In particular, if you have a lower bound for pseudopolynomial-time algorithms, it immediately gives a lower bound for approximation schemes. And so these things have been well studied. For example, a subset sum. If you look at 1 plus epsilon approximation algorithms for subset sum, partition, and knapsack, and you express their running time in the form number of items plus 1 over epsilon to the c, then right now we know the optimal exponent c for subset sum, it's 2. We don't know yet the optimal exponent for partition and for knapsack. It's narrowed down, but it's still a way to go. There's still a gap. Right. As I said, lots of other topics. You can look at scheduling problems. I mean, naturally, scheduling problems, you would want to find near optimal algorithms, but right now we don't know any. Integer programming, Jens and Rohwedder had some really cool results of conditionally optimal algorithms for certain classes of integer programming, but there are lots of other classes where this is still open. Let me ignore this, and then I'm done, right? Okay, so we have seen a couple of these applications here. In many, this partition and convolution approach is useful. That's why I wanted to show you this algorithm. And that's it. Let me stop here.
Thank you for the talk.